B star is coming by this. It satisfies argument of error A, B for all choices of A and B. So finding A and B is a problem. And then classification problem is also there, where you have the label. We are talking about a supervised learning problem. So previously it was regression as a supervised learning problem. Here classification as a supervised learning problem. So you are having the image set, for example, dog, cat, and cow, and we train an ML algorithm to learn the relation between the images and the label. So when we are talking about the images, we are talking about the actually it's three. It's n cross n. But if we talk about the black and white grayscale image, then it will be a prediction function from R m cross n to C, where C is the class set, which will be a subset of Z. But we can have unsupervised learning also, and unsupervised learning is it was already there in machine learning. People are using it. So basically what it does, we do not have the label of the data, but we have the data itself, and we try to find out the relationship between the two data points, and we try to classify them, find out the relationship. So for example, you have data set S in the domain omega x, and we are trying to find the relation among different regions of this domain omega x. So for example, we want to find out the group of the data. For example, customer segmentation, product association, fraud detection, and density estimation for a given distribution of the data. Those who knows probability, they know that if you know the probability density function or probability mass function of a distribution, then you can actually talk about the probability also. So finding the probability density function or probability mass function itself is a interesting thing to talk about the distribution. So here we are having the data set, and we can actually see that it is a k-mean clustering algorithm which we have used. So the data is also generated randomly, and we are in this figure, it is actually classified. So the data set is classified into three different classes. One is shown in yellow color, then it is sea green, and this is third color, gray color for me. So we do not know the label of the data, but we know the data is there, and we are just trying to find out or trying to segregate the data. Okay, and there are many ways, and some of the techniques like k-mean clustering or density estimation methods are there for unsupervised learning problem. Then you have semi-supervised learning problem, where you are having some data which is labeled and some data which is unlabeled. And then you have reinforcement learning. I do not know much about it, but it method belongs to the method belonging to this family of algorithm. They learn by rewards or penalties from the decision taken. Thus, a suitable path or policy is learned to maximize the reward. So basically here you are having sort of a rewarding system for each right decision. You will get the reward, otherwise you will get the penalization, which can be this makes the algorithm to learn. And these kind of methods are used to train algorithms to play games like chess or Go. Okay, reinforcement learning, I think, is self-driving car is also very much involved there. So already Professor Arvind was talking about what is neuron, who coined these words. So basically, mathematically, it's nothing but it's a node in the deep learning model through which data and computation flow. So basically, it receives input signal from the previous layer of the neural network and performs some component wise multiplication and scalar addition, and output the product and scalar addition to the next next layer of the neural network. So basically, you are having this vector x as input, x1 to xn, Rn vector, and you are having some weights associated with these vectors. You multiply them, basically it's component wise multiplication. Then you sum them and apply an activation function. Activation function we will see later, and then you just get the output and push it. So neuron will take the vector, multiply with the associated weights, and add something and push it to the next layer. Mathematically, it can be represented as y is equal to sigma applied on dot product of input vector x and associated weight. So, once you know the neuron, you can use this to construct a bigger neural network, and the simplest one of them is multi-layer perceptron, and its multi-layer perceptrons is artificial neural network, and it's an arrangement of neurons and non-linear mapping. Neurons we already discussed just now, it's just a unit, it's just one mathematical operation, multiplication between two vectors. One is input vector, one is the weight, associated weight. And the computing unit of this multi-layer perceptron is nothing but artificial neuron, which we talk about, and we stake them in the hidden layers. And F consists multi-layer perceptrons consist a fully connected dense layer that transform input data from one dimension to another dimension. And mathematically, you can say that it's a composition of alternating affine transformation and component-wise activation. So let us think like we are interested to approximate the given function f from space Rd to Rd, where small d and capital D are two different dimensions. And what we are trying to do, we are trying to use a MLP, calligraphic f, which is denoted by calligraphic f. Then the arrangement is as follows. And for preparing these lectures, I have taken the book Deep Learning and Computational Physics by Deep Ray and co-authors, and the images are also taken from their book. It is the preprint version is in archive, so you can download it and read it, but now they have given some new version, new edition, which is paid version, you can get it. So in the multiple layer perceptron, this is the architecture. So you are having 0th layer is a source layer, which has nothing to do, it just take the input, it just get the input from the user, and the last input is just give you the output. In between, all the layers are called the hidden layer. And this is an example of multi-layer perceptron with two hidden layers, and XIL is the output of ith neuron in the lth layer. So here you are having x0 as the input, you are having hidden layer, which means you are having neuron stacked together. You take this x0, multiply it with the associated weight vector, then you are applying the activation function sigma, and whatever output is coming, you are pushing it to the next layer, and then you are having output layer in this case. So in general, there are certain things which we should define. So let us denote by capital L the depth of the network, so like number of the hidden and computing layer. HL is the width of the layer, it is the number of the neurons in the layer L, and total numbers of layer is L plus 1, where H0 is your input layer, which is source layer, and output is H capital L plus 1, which is your output layer. And XL is HL dimension vector, and it is coming from the Lth layer, and it serves as an input to the next layer. The input signal is x0 is nothing but the vector in Rd, where D is small letter dimension, and ith neuron of L, layer L, what it does, it performs the affine transformation on the layers of the input vector and followed by the non-linear transformation. So basically what it is, you are having this is your input to the layer L, and you are multiplying it with the W, the weight vector, weight and bias, and the bias is B, and you are getting the output XL for the next layer. So WL and BL are called the weight and bias associated with the ith neuron of the layer L respectively, and sigma is your nonlinear activation function. And if you have this notation in your mind, then you can actually write the whole layer 1, this layer, as XL equal to non-linearity applied on A matrix A dash applied on the input vector x l I minus 1, where al x I l I minus 1 is defined by this expression, and we are applying the activation function as component wise manner. So that you can actually write the entire neural network as given by question number 3. It's a alternating affine transformation and component wise activation. So this is your x, which is input. You apply one affine transformation, apply this non-linearity, again you do the same thing recursively up to the last layer, and this activation function can be different in different layer. You can in fact apply the different activation also for different neuron if you are really very much keen to know what is happening. So basically this is about the mathematical representation of the neural network as a affine transformation and component wise activation. So what I think you must have understood, there are some parameters. Parameters are nothing but the weight and bias in the neural network, which we are representing here as theta. And how many parameters are there? There are total n theta parameters in the underlying network. And so with this setting, we are doing is we are f x theta. It represents a family of parameterized functions where theta needs to be suitably chosen. The target function fx at the input x. So basically, you are having this network represented by this calligraphic f x theta. Theta is a parameter. You want to choose them such that whenever you give x, it gives you a proper output, required output. Lunch was heavy. So we basically everything boils down to find out suitable theta. We will see how we are doing that, but we are having some more point to discuss before we actually go and try to find out how to find theta. Like first thing is like what are the activation functions we can use, what kind of property should be there in the activation function. So first and foremost property is like the activation function should be non-linear, so that you can actually deal with the non-linear problems also. So it will introduce the non-linearity in the networks, and it then allows the learning of complex pattern and relationship, so that it can model the complex functions. And it is required to be differentiable because the backpropagation algorithm which we use requires the derivative of the loss function with respect to the nonlinear activation function also. And it should be computationally efficient. Computationally efficient, everything is good. So activation function should also be computationally efficient. So there are various nonlinear activation function. I have some of them on these slides. So one is ReLU. So it is called rectified linear unit activation function, which is nothing but when you apply this activation, it gives you maximum of 0 over the input vector x. It is simple, fast, and it reduces the vanishing gradient issue. Vanishing gradient issue I will discuss little later, and it is also having a problem. It is called dying ReLU problem. I will discuss that in my next slides. Then you have sigmoid function. It is smooth curve and it outputs always between 0 to 1. Again, it has the problem of vanishing gradient for large or small inputs. Then you have 10H hyperbolic tangent nonlinear activation function. It ranges between the interval -1 to 1, and it's centered around 0. And again, it suffers from vanishing gradient problem. I am using this word vanishing gradient problem purposefully so that it can hit your mind when I come to resonate. Then you have new activation function, not very new, but yes, in machine learning it's quite old, like in deep learning, the way the field is advancing. So these are the nonlinear activation function, and one special activation function is called softmax. which is used in the output layer of multi-class classification. So this is a special kind of activation functions which actually converts logics into the probability, and it is used in the multi-class classification. So if you draw the activation function, these are the plots. So sigmoid is from 0 to 1, tan h is from -1 to 1, ReLU is 0 and then positive x, and then LIGReLU, ELU and swish. So there are different activation functions. There is a plethora of activation functions available in the literature. If you want to use them, you can actually see for what purpose they have done. From my personal experience, if you are working with the a regression problem, if you are having the smooth functions where you are trying to approximate, tan h works fine. But if you are talking about discontinuities or sharp edges, then ReLU is much better for learning. Yes. So since we know what are the nonlinear activation functions, we can talk about their derivatives also, because this is coming to disturb us again. So sigmoid function is defined by fx equal to 1 over 1 plus exponential minus x, exponential to power exponential minus x, and then the derivative is given by this function. ReLU and its derivative is here. Hyperbolic tangent and its derivative is given here. Okay. Leaky ReLU derivative is also given. So these are the expressions for the leaky ReLU. F dash x equal to 1 if x is positive, otherwise alpha if x is less than 0. Softmax function and derivative is nothing but a Jacobian matrix, and in matrix form you can write it del f by del x equal to f times 1 minus f transpose, where f is a softmax vector. But why we are discussing this? I am discussing it so that I can show you the derivative. So you can see that if you are having sigmoid activation function, then its derivative is achieving maximum value which is lesser than 0.25. Here also in tan h the derivative is going up to 1, but most of the time it will be between 1 to 0. ReLU activation function, either it is 0 or it is 1. Leaky ReLU is also having similar phenomena. So what I am trying to say that if you are using the derivative in your calculation, whatever your input, the maximum value which you can obtain is 0.25 if you are using the sigmoid function. If you are using tan h, you can go up to maximum of 1. So as I discussed, like there are two type of problem. One is regression, another one is classification. So if you look at the simple MLP network, so this is your input layer. I am taking only one hidden layer in this figure. One hidden layer is there. Here you are passing the input vector vi, and you are getting a real value outside at the output. It is a regression. So basically it's from Rn to R mapping, like basically R5 to R. This kind of network we have used in our own work, where we try to learn the fifth order Venn reconstruction. And this is the classification networks, which is actually again taking a vector from R5, a 5-dimensional vector, and then it is giving you 3 different states as a classification. So you have input layer, then the hidden layer, and you will get the output. This output is called logits of the network. We apply the softmax so that it can become the probability. So each node here will be representing, it will be giving you one hot vector kind of scenario, and then you can talk about the loss, classification loss. So these two type of networks are there. I have taken this figure because we have used them in our own research work. So once you know the neural network mathematically, how to do it in Python. See the now one thing which you should understand, that large language models are really very good if you know what you are trying to do. So you can actually prompt them and it will give you the proper code. You just have to cross check whether it is doing properly or not. You should know what is right, what is wrong, and you can do it. So like how to define a neural network in any API like TensorFlow or PyTorch or any of other MXNet. You can simply prompt in any large language model and it will give you how to do it. So this is also one prompt output. Like I wanted to define one neural network with 50 neurons in a hidden layer and I am trying to learn a mapping from R to R. It's a regression problem. So in PyTorch we can do like this. So in PyTorch you have class which is inherited from the NN dot module of the PyTorch. So once you define this class net with NN dot module, you have all the functionalities available to you. All these methods are defined there. Probably in the afternoon session when hands on there, Anuradha may talk about it or I will discuss with you. Okay. So we talk about regression problem and classification problem. Okay. So you might have heard about the terminology MST loss, mean square error loss, when we are doing neural network, or cross entropy loss. These are the two terms which you know, and we use them as a black box. Here I am trying to understand from a statistical point of view why they are good. So basically whether you are doing regression or you are doing classification, what you are trying to do, you are trying to learn the distribution of the data. If you understand the distribution, then you can predict the output for an unknown input data also. So everything boils down to finding the distribution of the underlying data. Okay. And in probability and statistics, people have used these things to find the distribution. So MSC loss, let us see from the maximum likelihood estimation point of view. So like you are talking about a regression network where f is the underlying function. Oh, sorry, it's a neural regression network. Okay, so f is, I think I need to change this notation. X is the input vector and theta is the x theta. Let us see fx theta. F is not a function. Now it's a neural network, regression network, and theta is the parameter of the model, weight and bias of the neural network, and the output of the predict network fx theta is the predicted value for the regression tau. So you are having a regression problem for fx, like some function phi of x equal to y. Okay, where x is coming from RD and y is maybe coming from R. So what we are trying to do in regression, that we are trying to learn the parameter theta here, such that the model predicts the value of y as accurately as possible. And to do this, we can approach the philosophy of maximum likelihood estimation. So what we are having the data. So we assume the data follows some distribution. We do not know the distribution, but we follow, and we assume that data is coming from the Gaussian distribution, because if the data is large, by the central limit thing, a large law of large number, we have the result that it is following the normal distribution. So we assume that the target variable y follows a Gaussian distribution given x, like y given x follows the normal distribution with the mean fx theta and variance sigma square, where this is your predicted output, mean of the regression network, and sigma square is the variance. For example, y can be mean plus epsilon. Epsilon is nothing but the noise which is coming, it's a random variable sampled from the normal distribution with mean 0 and variance sigma square. So if your data is like this, so basically you are assuming that your data, output data, is having this like it is following the distribution which is given by fx theta mean and no sorry yeah, this is following this mean of the normal distribution fx theta and epsilon is the noise. And once you know this, then you can talk about the likelihood of the observing of this data, like for what input, what output, whatever data you are having, you can talk about the Gaussian product of the Gaussian probability density function, which is given by this expression. So you are just multiplying the Gaussian probability density function with mu and variance sigma square. Since we are assume that mean is here fx theta, so we are taking fxi theta sigma square. And once you have the product, you can talk about the log. So then you can talk about the log likelihood, and you can further simplify it to this expression log of the loss function theta, loss function of theta, and these two terms will come. The first term is like stationary, do not have to bother about it. The second term is there, and what we are trying to do, we are trying to maximize the log likelihood. So when you want to maximize, since there is a negative sign, you will be trying to minimize the negative log likelihood. So you are trying to minimize this summation, which is nothing but mean square error. So when you are training a neural regression model and using MSC loss, what you are trying to do, you are trying to maximize the log likelihood of the given data prediction. And this means that the maximum likelihood estimator or estimation for regression is equivalent to minimizing the mean square error loss function, which is widely used for training regression models. So now you know why we use MSC loss. Okay, MSC loss you have seen when you are talking about the regression in non-probability way also, non-probabilistic point of view also, but here we are having that viewpoint, like you are trying to maximize the log likelihood of the underlying observation. That means for the given x, this is our maximum likelihood possibility for y. The second is classification network and the cross entropy loss. So again you are taking fx theta as a classification network, and x is your input vector, theta is parameter, weight and bias, and the output of the network is a probability distribution over the classes. Okay, so you are having different classes, you are getting some prediction. The prediction will be like it is dog or cat or mouse, and there will be some different probability, like with this much probability or confidence the neural network is predicting that it's a dog. Or so basically you are talking about the probability distribution over the classes. So what is our objective? So the objective is to learn parameter theta such that the observed data follows the distribution predicted by the model. Okay, so you have the data and your model is also predicting. Data is coming from some distribution, your model should also mimic that distribution. So basically the idea is that this true probability distribution is nicely approximated by the predictive model which you are having, the classification neural model. So this is your predicted probability distribution of the output y given x with the parameter theta, and p true is the true probability distribution of y given x. So here the only thing which is not known is the parameter theta, and we want to learn that. So basically there is a concept called KL divergence theory. In information theory people have used it. So basically what we are trying to do, you are having a probability distribution which is coming from the underlying data, true probability distribution, and this is your model, what it is predicting. You just want to minimize the gap or distance between them. So you are trying to closely train the model so that your predictive distribution is also similar to the underlying distribution. So KL divergence basically it minimizes the difference between the true distribution and the predicted distribution, which represents probabilities. So classification network basically talks about the probability when it comes for the output vector. So KL divergence talks about like KL divergence of probability distribution P and Q, where P is the true probability distribution of the output Y given the input X, and Q is the predicted probability distribution from the model. So if you minimize this, you basically you are improving the model prediction. So when you minimize that, your P, which is Q, which is the predicted probability distribution, is closer to the probability distribution P. This is what our objective is. So when you talk about the cross entropy loss, it comes from the KL divergence theory. This KL divergence loss. So basically, you using the log function, you can write it minus summation of true probability distribution multiplied with the logarithmic of predictive probability distribution by the model. So basically, if you minimize this, you are minimizing the KL divergence between the true and predicted distribution. So whenever somebody asks you why you are using cross entropy loss, the idea is that cross entropy loss minimizes the KL divergence loss. KL divergence loss minimization means you are trying to bring two probability distribution closer, minimizing the distance. I am using this word distance, but minimizing the difference between two distribution. So that's why we use cross entropy loss. Then we have some UAT. There are many universal approximation results. These are also for the same book. So basically, when you are using neural network, you want to have a kind of a confidence that this is going to approximate the function, underlying function, or it is going to learn that. So some confidence is required. Confidence comes from the theorems, mathematical theorems. So this is a result by Pincus in 1999. It is called paper Approximation Theory of MLP Model in Neural Networks, and it got published in Acta Numerica. And what it says, like if you have a set K, subset of RD, which is closed and bounded set, then if your function f from K to R, real valued function from K to R is continuous function, then for a given epsilon, there exists an MLP with a single hidden layer with arbitrary width h and non-polynomial continuous activation function sigma, such that the maximum norm of the predicted value of the neural network for given x minus fx is less than or equal to epsilon. So basically, if your function is satisfying this continuity condition, then there is a neural network. It does not talk about what with the width of the neural network. It is not going to talk about which nonlinear activation function you are using. It is just giving you existence of a neural network which can approximate such function closely for any given choice of epsilon. Okay, you change the epsilon, then your hyperparameter. So basically, width of the neural network, depth of the neural network, learning rate, all these are hyperparameter, and if you change the epsilon, your hyperparameter will also change, but there will be a neural network which will be able to satisfy this inequality. And then this is another theorem which talks about function f, which is from K to RD. So basically, it's a vector valued function, and it's a continuous function. Continuity is mentioned here. Then given an epsilon greater than 0, there exists an MLP with arbitrary number of hidden layers L, and each should be having the width bigger than small d plus capital D plus 2, where small d is the dimension of the input vector and capital D is the dimension of the output vector, then plus 2. So at least something it's giving at least the lower bound of the width of the hidden layers, and a continuous activation sigma, and there are some other conditions. You can see the paper. Then you can have a very close approximation of the true value with the predicted value of the neural network. And the third theorem is again, it is talking about a function which is actually continuous, not only continuous, but it has having two continuous derivative. That means f is C2 function. Then consider an MLP with ReLU activation, and h is bigger than, h is nothing but the width of the layer, each layer, greater than equal to 2D plus 10, then there exists a network with this configuration such that the error converges as. So basically it is giving you a bound on the convergence. So if you are having a C2 function, then you can use a neural network MLP, and you can achieve this kind of convergence where C is a constant which depends on the number of network parameters. Network parameters is weight and bias. Okay. After all this jargon, let us see how actually we do. If the data is given, first thing is that once, if you start working with the neural network, suppose any point of time of your life, or even if you are doing it now, you know that whenever data comes, it is required to know clean the data, reprocessing the data, how to segregate the data for learning process. So there are certain steps when it comes for the training, validation, and testing of neural network. So you are having the data set capital S or Gothico S, and data is coming from the function f, target function f from x to y, and we wish to approximate the function using the neural network. Calligraphic f, input vector x, small theta is your weight and bias, and capital theta is your hyperparameter like depth, width, and learning rate. So this is your data, and this is your network which you want to use to learn the function f. So the design it involves some steps. First step is divide the data set into three parts: training set with n train sample, validation set with n value sample, and testing set with n test samples, such that n equal to n train plus n value n plus n test. So if you have seen the physics informed neural network, there we are not doing this. Physics informed neural network, you are directly trying to satisfy the PD loss and the boundary condition you are satisfying there. So this kind of steps are not required there. Okay, you are not. So physics informed neural network is sort of semi supervised learning. So you have initial condition data, boundary condition also you know, so that data is known, but within the domain the data is not known. There you are talking about the PD loss. So basically this way you are having the full domain. Some place you have the data, labeled data, and some place you do not have the labeled data. So it's semi supervised approach, and these steps are not required there. So don't get confused. I'm just talking about the learning, deep learning. Whatever I have discussed, it has nothing to do with PD so far. It will be used in PD, but it is generic. So so we have divided the data into three different categories: train data, validation data, and test data. And once you are talking about the neural network, you have to talk about the loss function. So here we are denoting the loss function by capital pi. So there will be different type of loss. One is your train loss, another is validation loss, and test loss. So first thing is that you have to find out the weight and bias, good weight and bias of your neural network. So you find out the optimal value of theta star, and how you can do that? You have to minimize the loss. Loss can be various kind of losses are, but I discussed the regression MSC loss and classification cross entropy loss. So minimize those two loss if you are working with the regression or classification. So if you minimize those loss, so basically the minimum of loss for the given theta is theta star. This is your optimal weight and bias. So once you got the optimal weight and bias, then you have to talk about the hyperparameter. Hyperparameter can be obtained by the grid search. So basically, you try different kind of width, depth, and find out suitable hyperparameter capital theta, and then you can test the performance of the resulting network on the unseen data. Unseen data is nothing but the data which you kept for testing, because validation data is also shown to the neural network, because the idea is that you minimize the train loss and save the model for which you have the best validation loss. So validation loss is already taken into account by the model. So if you want to test the model, you have to test the model on the third data set, not on the train data set or validation data set. You have to go for the test data set. So there is one, so life is not as rosy as we think. So when you are having all these things, and if you start training the neural network, you may encounter various issues, like your train loss is working very fine, but your validation loss is not decreasing, and test loss is also not coming very nicely, though you are hitting the 100% accuracy in the train data. So that is called overfitting in the deep learning terminology. So data overfitting problem. So often models with small values of train loss and validation loss does not ensure that the test loss will also be small, even if data is not OOD, out of distribution. So in order to deal with this situation, we have regularization technique. Regularization is in all the APIs like TensorFlow, PyTorch, if you define inbuilt, inherently they are applying the regularization. So you really do not have to hard code it into the model, unless you are not really very much into the research and trying to find out some other technique for the regularization. For example, if you are working on the research problem, how to regularize the neural network, and you want to code it in the code, then you have to do it. Otherwise, modern API will do it, Gemini will do it, ChatGPT will do it for you. So regularization, so basically MLPs are often over parameterized. So like you have a lot of weight and biases compared to training sample. You can have 10,000 training sample, but you can have million weight and bias in your data. For example, if you are working with the image problem and 1,000 images are there, and but you are using network with billion or million at least weights and bias. So basically your n theta is always, most of the time, is very bigger, very large compared to the training sample, and it results to highly nonlinear network, and the loss function can have many local minima, and this is one problem. So let's just consider this one particular example. So you are talking about the output of ith neuron in the layer L, so which can be represented by this expression. So basically you are having the j is indexed for all the neurons in the previous layer, and whatever vector is coming from that, it is denoted by xl minus 1. You are multiplying with the weight wij l, and then you are applying the bias, adding the bias and applying the non-linearity. So if you talk about the derivative of this xil with respect to the vector in the previous layer, then you can see that it is actually proportional to wiil. So basically when you will talk about the back propagation, this kind of term will come there. It's a chain rule of differentiation, partial derivative. So this type of term will come. So basically it is proportional to the weight. So in case if this weight is very big compared to 1, then your neural network would be very sensitive to the small change in the input vector xi l minus 1, and it is a ill-posed network. So if your weight is large, when you are learning the weight and bias, and if your weight is very big, then because of this big magnitude, a small change in the input vector will make your network to predict something else, which is not correct, and it is called the ill-posed nets. So the idea is that theta should be good. So the norm of theta should be small. So basically, it is known fact that regularization increases the selection of minima corresponding to smaller value of the parameter theta. So for example, you have loss function landscape. Red is with no regularization, and the green one is with the regularization. So if you see the red color loss function landscape, then which theta is the optimal theta? This is the axis of theta. So this theta is giving you this loss, this theta is also giving you this minimum of this loss, this is also minimum of this loss. So the idea is that you regularize. If you regularize the same thing, you will have the loss function which has this blue green color landscape, and then you can decide upon the optimal theta star. And as I said, if your theta is very big, your network will be sensitive to the small variation in x. So this is a x-axis. You are doing small variation, and your network will start giving you prediction which are fluctuating in nature. It is instability. And if you regularize the neural network, basically what you are doing, you are enforcing that a neural network weight and biases should be small. The norm of them should be less than equal to 1 technically. Then your network sensitivity will be very smooth. You can change the value of x, but network will not go. So it is making ill-posed network to well-posed network. And the common regularizations are the simple method of regularization involves augmenting a penalty term to the loss function. So you have a loss function, and you are putting a penalty function alpha times norm of theta square. So basically, you are minimizing the norm of the weight when you minimize this loss function. So L2 regularization, you are having that 2 norm for the weight, and LA L infinity, I think it's L2. I think this is L1, maybe L1 regularization. So here you are having mod of theta I. So what you are doing, when you are having this term added to the loss function, then when you minimize the loss function, you are minimizing the norm of the weight and the bias also. Okay, so small weight and bias are good, small normed. Okay, weight and biases are good, and let us see how basically when you define a neural network, how you can initialize the weight and bias of the neural network. So there are some known techniques, but some mathematics behind it is given by this theorem. So let your xi's are the random sample from a population with mean mu and variance sigma. Then expected value of mean is equal to mu, where mean of x bar is nothing but the mean of the sample, and variance is given by sigma square by mu. So x bar is sample mean, and capital S square is the sample variance. So this is your theorem, which comes from the probability statistics. If you don't know this, so basically you are having the variance which is sigma square by mu. Sigma square is the variance of the population, and mu is the mean of the population. But now we are talking about the variance of the sample. So when you are talking about the neural network, its weight and biases should satisfy certain criteria, as I said. So its variance should be less, small. Okay, small variance. If you go for the estimator theory, consistent, sufficient estimators are there, and one of the properties that your variance should be also low. It's preferable. So how we can do this? So let random weight WIR randomly sample from the normal distribution with mean mu. So I am giving you one example where we are taking the weight which are coming from the normal distribution with mean 0 and variance or standard deviation variance 1. Okay, and let us assume that these weights are associated with the neural network with n neurons, and they are connected from lth layer to l plus 1th layer, and output is this y equal to sigma times input vector into the weight. So you are having this input vector, here are weights. If you multiply them, and you will get the output y. So if you denote this z by this product of input vector with the weight, and if you take total n equal to 225, okay, and if you are taking all one vector for every xi, it is equal to 1, then your mean of the z will be 0, but variance of z will become very big. Time is over. Okay. So variance of the z will become very large, which is not preferable. So though your weight is following normal distribution from with mean mu and variance 1, but your output variable will follow the normal distribution with mean 0 and variance 225. So this will make it not a good. Thus the standard deviation of z equal to 55. Clearly it is highly likely that the value of z is always very big. So the modulus, or so if you talk about in terms of weight, then it is always very bigger than 1, and if you are taking the activation function sigmoid, then what will happen, since the mod, so if you take this z, so it will be either 0 or it will be 1, because you are going to get most of the time a value of this output variable z as very big in modulus greater than very large compared to 1. So that's not a good thing. So basically your activation function is sensitive only in this area. After that it is giving you constant value 0, here it is giving you constant value 1. So if your output vector is falling here, whether it is coming here or here, the output will be same. So that's not a good thing. So we try to minimize this. So shall we take a break now? Tea break. So we'll again resume from here. Okay. So you can stop it here. No, you can stop the recording. We are taking tea break. So we were talking about the variance of the weight, and we have seen one example where you are just giving all one vector as input, and your weight is initialized from the normal distribution with mean 0 and variance 1. Then we saw that the output vector z, which came out, was having magnitude much larger than 1, and if you apply a sigmoid activation function or tan h activation function, because of this large magnitude of the output vector z, you are going to lose a lot of sensitive information. So it is always good to avoid such situation, and we minimize the variance of the weights so that we can prevent vanishing and exploding gradient during back propagation, and speed up the convergence by facilitating efficient optimization, and we ensure the symmetry breaking. No neurons learn distinct feature. So neurons learn distinct features. Basically, what we want, each neuron should learn different feature. It should not be the case that lot of neurons are learning the same feature. That is not a good no, efficient way of doing deep learning. So there are different strategies for weight initialization. So you can start with the zero initialization and then start back propagation algorithm and keep on learning the weight. You can do the random initialization. So there are problems, benefit and problems are also there for each kind of initialization. But one of the popular initialization is the Xavier's initialization, and what it does, it forms it initializes the weights following the uniform distribution with the in the interval minus under root 6 by n in plus n out to under root 6 divided by n in plus n out. So basically it's a fan in and fan out number. N in is the number of the size of the input vector or number of the neurons in the previous layer, and out is the number of neurons in the output layer. So this is n in and n out. So you can use this network with mixed sigmoid and tan h activation. Then we have E initialization. Again, it is uniform distribution with the different intervals, like the weights are sampled from different distribution, or it is, you can say that it is sampled from the normal distribution with mean 0 and variance under root 2 divided by n in, and it is preferred for ReLU and its variant. LeCun initialization is also there. Let us skip it. And then you have bias also. Weight initialization we saw, and bias is also there. So it is typically initialized to 0 or small positive constant. So practical considerations are also there. You can do the layer wise initializations, like in one layer you take one strategy of initialization and another layer you take another strategy of the initialization. You can take pre-trained model also. It is called transfer learning. So where you have neural network trained on already on, suppose you talk about the ImageNet data set, you have trained the neural network like VGGNet on ImageNet data set, and no, on image data set, and then you want to use it for some other thing specifically to your images, then you can take the weight of pre-trained model, and then you just train the classifier weight to get a model fit for your customized data set or particular data set. And you have PyTorch and TensorFlow APIs which can help you to do these things, this kind of experiment. So like in JVS initialization, so you have defined the class net, which is inheriting the methods and modules from nn.module module of the PyTorch. Then you have this constructor, and you are using the super init function, and you had defined here, these are like Python terminology. So basically it's constructor function, and you are using super method to initialize. So basically what you are doing here, you use the init of the inherent class of the nn module. So you are defining the fully connected layer 1, what it is having 784 input dimension and output dimension is 128. We can say that it will take a vector of 784 length and it will output a vector of 128 length. Then FC2 you are taking this in output as input and then you are putting into 10 output. So basically it's this network is designed for MNIST data set. I don't know, MNIST data set. Number like 0, 1, 2, 3, 4 up to 10. So you have up to 9. So you are trying to identify the digit in the handwritten transcript. Then you are passing X into the fully connected layer FC1 and you are applying the ReLU. ReLU is defined the model F which you have to import when you define this, and then you are again passing this output after applying the ReLU to the second layer and you get the final output. And you can initialize the network by calling the function, defining the instance model with this class net, and then you can actually define a method in PyTorch or Python which is doing this JVar uniform initialization. So all these things are already defined in PyTorch and you can have a method from there and you can initialize, and you are applying this method defined by you to initialize. So this is the way you can do in PyTorch. If you are not able to understand it from here, if you don't know Python or PyTorch, you can try with the Gemini AI and it will give you these things clearly. So these are the summary table, benefit and what are the initialization technique, what are the formula, underlying formula, and what are the use cases. So let us look at the loss function, which is the hero of the entire story of machine learning. So your pi theta is the loss function where theta represents the parameter, weight and bias of the neural network, and it measures the error between the predicted output by the neural network and the target output y. So y is known to you and you are just trying to measure the difference or error between these. So what we are trying to do, we are trying to minimize the problem, finding the optimal value of theta star or theta, which is denoted as theta star, which is going to give you argmin of the loss function over all theta, all possible theta during the training step. So you have the method called gradient descent method, where you can actually which is actually being used for finding the good theta star. So you start with some random theta or initialize theta, whatever we discussed, and then you keep on doing the back propagation using gradient descent algorithm. So if you take your loss function pi theta and if do the Taylor series expansion, you will get this expression, and for some theta hat of small neighborhood of the theta 0, and if we assume that grad theta is small and the second derivative of the loss function is bounded, then you can actually give a very good approximation after neglecting the second order term. So your loss with the initial weight plus small increment in the weight is nothing but approximately equal to the loss at theta naught and the gradient of loss function evaluated at theta naught, the initial weight, times delta theta. So what we are doing to minimize this loss at theta naught, we minimize this grad theta equal to difference of new loss minus the old loss, and the idea is that you take the small increment in theta in the opposite direction of the gradient. That means delta theta is equal to minus sign of the gradient of the loss function with respect to theta, into eta, where eta is a very small step size. It is termed as a learning rate. So, if you see the gradient descent update formula, so the new weights are nothing but the old weights minus eta times the gradient of the loss at the previous loss or previous weight, and here eta is the learning rate, and it actually guides the updates in the steepest descent direction, and it actually ensures stability and convergence. This is the result. Again, you can see from the book which I told you. So, this is one of the this is the method which people use in your network training. When they talk about the backpropagation, they talk about the derivative of the loss function with respect to the weight, bias, non-linearity. And for example, if you take this loss function theta minus 3 whole square, and then its gradient will be 2 times theta minus 3, then update rule will be this formula. It is similar to the Euler formula. So, if you take the learning rate 0.1, then if you do this iteration, what will happen? You know that the unique minimizer of this loss function is theta equal to 3, then it will become 0. So, when you are doing the iteration, as you keep on doing the iteration, it is first order method. So, you will see that the your value of theta star, theta is approaching to theta star, which is equal to 3. So, this is the iterative process. You can write a small program for doing this. It can be done in MATLAB also. So, I will skip this part. How we actually do the gradient using the backpropagation, how to calculate gradient using the backpropagation. So, what actually we need the gradient of loss function with respect to theta, or more precisely when we are talking about this, we are looking at the gradient of the loss with respect to weight and bias, and we can see that the output of layer output vector x in the layer L plus 1 is given by affine transformation, and then you apply the non-linearity. So, affine transformation is the input vector multiplied by the weight plus bias, and then you are applying the non-linearity to this affine transformation, which is denoted by here zeta. Yeah, and if you can understand, like if you recall from the previous previous presentation, we have taken the notation where AL calligraphic AL applied on input vector x in the coming out from the L minus 1th layer, then your zeta I in the Lth layer, the affine transformation can be represented by the equation number 4. So, basically when we are training the neural network, you have two things, one is forward pass, another one is the backward pass. So, forward pass is the lower line of this computational graph, the lower members of this computational graph. So, you are having the input vector x naught, you apply this affine transformation, you get zeta 1, then you apply the non-linearity sigma, you get the output for the next layer. This is your x1. Again, you keep on doing this, ultimately you will get the output in the last layer xl plus 1, which is your output layer. Then you calculate the loss. Once you calculate the loss, you talk about the gradient of the loss with respect to the previous or this output. Then you go by the chain rule of the differentiation, and you keep on doing that, and you ultimately you will get gradient of the loss with respect to zeta, gradient of loss with respect to each vector input or output vector xi, and this is the way you can actually calculate. So, this is the forward pass. You evaluate xi and zeta l or xl and zeta l for each layer, and then you calculate the MSC loss, and then you do the backpropagation. So, how you do this? So, basically it is a computational graph, everything is implemented there. Chain rule of differentiation, I think you know, but when it comes for the neural network with large number of weight and bias and vectors, then it becomes difficult to do it by hand, understand. So this is the representation or like mathematical expression, but you cannot do hard coding for this. So you have to rely on the API which you are using. Automatically it will do it, but underlying mathematics is given here. So for the computational graph, it is easy to see how each hidden variable in the network is transformed to the next, applying the chain rule. So you are, look at this expression number 5. So you are calculating the loss of gradient of the loss with respect to zeta L. So it can be represented as gradient of loss with respect to the output layer vector, then partial derivative of output layer vector with respect to the affine transformation zeta L, then affine transformation out partial derivative with respect to the previous layer XL, then you are having non-linearity also will be there. So this is the expression, you are doing the chain rule. So in order to calculate the loss of the neural network, minimize the loss of the neural network, you need backpropagation. For backpropagation, you need the gradient of the loss with respect to each weight and bias, which can be computed. So this graph is very much important for the code to learn. Then you can actually calculate the gradient of loss with respect to weight, which is given by the equation number 6, 7, 8. I think it is going here. So it is by the equation number 10. So for gradient of loss with respect to weight matrix W in the layer L is given by the loss of the gradient of loss with respect to affine transformation in the Lth layer, and then the gradient of a partial derivative of this affine transformation with respect to those weights. So it's a little bit complicated, but it is simply nothing but the chain rule of differentiation. So if you look at the example, I think this example will not work here. I will skip this example because my code, okay, let me check if it is working or not. It's not properly mapped, so I'll not run this. So you are having X and you are trying to find out Y hat. Your input is X. You have two hidden layer, one hidden layer with 2 neurons, and if you do the back propagation, so you are, this calculation actually Z11 is the output of when you multiply the input vector X with the weight W11 plus B1, and loss is given by the output vector, the target output vector Y minus the predicted vector Y hat. And then this is the update rule. I think this, I will share this, you can understand the calculation by yourself. And let us go to the optimization method. So basically we understand how to calculate the loss and how to find the gradient of loss with respect to weight and biases. Then how you can actually minimize, because if you take the entire data set in one go and try to use this backpropagation, it is computationally very inefficient. So there are people who have designed or come up with the new ideas. Everything is a version of backpropagation algorithm. How you are doing this? Stochastic gradient descent is nothing but one version of backpropagation. So you have a optimization algorithm like stochastic gradient descent. This is momentum and Adams. So Adams is quite popular because of the fast convergence, as per my own experience. So these are all are nothing but efficient algorithmic way to minimize to update the weight and biases using the gradient descent approach. So in the stochastic gradient descent method, instead of calculating the gradient of the loss function over the entire data set, we compute it over a single data point or a mini batch. The update rules is as follows. So basically you are having the new value of the parameter in terms of the old value of the parameters minus learning rate multiplied by the batch wise gradient loss. So it's a gradient of the loss function phi theta with respect to theta evaluated for the data point xi, yi. So for each data you are calculating and updating the weight and bias. Then you have momentum. So momentum is also one version of stochastic gradient descent method, improved version. So it is a optimization method that accelerates stochastic gradient descent by maintaining a running average of the past gradient. So you are having beta is the moment of, so Vt, the update rule for the momentum is Vt is equal to the previous weight, no, Vt is basically a momentum. So you are taking beta momentum in the previous step and in the new step, and then you are updating your parameter at the next level using the parameter value in the previous level minus eta times the running average of the past gradient. Momentum, so there are some advantages and some disadvantages of this momentum method. And then we have Adams optimization method. This is again adaptive learning rate optimization algorithm which combines ideas from both momentum and RMS prop, root mean square propagation. So I'll skip this. The formulas are given here. So I'll go through one or two codes which shows this before we close this session. I would like to talk a little bit more about the classification thing here, or I think I can skip it. So let us go to one code for the regression problem. Yeah, how we can implement it in the PyTorch. So this is your Google Colab notebook where I generated this figure. It's a regression problem. So basically what we have done here is, how many of you know PyTorch? Raise your hand. You know PyTorch or Python? You don't know? Python is a snake. Okay. Cobra is also one. So basically in Python is preferred language for many of the machine learning people because you have a lot of APIs, modules available, developed like NumPy is there, Matplotlib library is there, scikit-learn is there. So many modules are available in open, so people are using it. Okay, and a lot of community support is also there. If you have any problem, you can post in the relevant board and people can answer you, those who are enthusiastic or doing the work. So basically what we are doing, we are just randomly generating the data because our machine learning is what? You should have some data, then you try to fit the model. So here we are not talking about the deep learning method. We are importing the NumPy. NumPy is the linear algebra library which handles with the vector and matrices in Python. And then you want to plot, so you are using the pyplot method of matplotlib library and you import them. Then here we are generating the random data, and for the reproducibility of the data we need to set the seed, random seed. So here it is set with 42. Then we generated x, the x data where you are generating 100 random number between 0 to 2, and then you are taking a linear line y equal to 4x plus 3x plus you are adding some Gaussian noise, so that data is not on the line, you have some noise in the data, and then you try to fit. If your data is already well behaved linear, then there is no issue point to really go for the machine learning. Then we are going to use the linear regression method of the scikit-learn library. So we import linear model or linear regression from the linear model library of the scikit-learn, and we create one instance of that class linear regression, and the once you created the instance, you can actually use to fit this with the given data x and y. And the moment when you did do it, your instance is the model, it is trained by the in the scikit-learn immediately, and then you can generate a new data point, and you can use this learned linear regressor to predict the new value, and then you can run the you can then do the prediction. So let us if I run it, it will take some time, and you will get this. So this is your regression line and this is your data. So you can do this scattered plot where your data x is in 2D, so that you can see this data in two-dimensional case, scattered plot, and you can show the line, the regression line, by predicting the new data. So basically what we are doing here, we are taking the new array, x new is a new array which is between 0 to 2, like first point is 0, second element is 2, and when we are doing the prediction we are getting this, then you are just plotting this. So basically your x is 0 and 2 and y is your predicted value, two values. So then you can just do the plot between x and y and it will give you a line which is your regression line in this case. And then this is the unsupervised learning figure which I shown there. So again here we are using the method from scikit-learn cluster k-mean clustering algorithm, and you just generate the random data of 100 times 2. Basically it said 100 cross 2 data. So basically 100 row and 2 columns data. So it's basically it's a matrix, and then you just simply invoke k-mean method, and you are defining like give 3 clusters for the random state 42 and then fit the model. Then you can use the techniques, already defined methods in the k-mean method of the scikit-learn, and you can do this plotting. I think this is here we are actually we want to plot it, so we are creating a mesh grid. Mesh grid is nothing but you give one-dimensional array and you do the mesh gridding, it will give you 2D array of the same number, so different coordinate. So when you do want to plot, it will help. Have you used mesh grid in MATLAB? It is there in MATLAB also, mesh grid, for plotting 2D plots. And this is the plot. Simply you are just using the matplotlib libraries and you are putting the scattered plot, and it will show you these figures. If I put here, if I run here with 3 classes, I am getting this figure. If I put here 4 classes, what will happen? Number of cluster. I want to segregate the data in 4 cluster. It is happening like this. So it is giving you some data is coming on the boundary point. Okay. So this is simple classification regression. It is not deep learning, it is just machine learning. Okay. And these are the functions which I wrote for plotting the activation function which I shown you. Okay, it is simple as you do in MATLAB. And this is your backpropagation algorithm code. I will share this code with you, but I don't know how much it will help you. But it is to show various kind of scenario. And let me see if I can have some code on some of, maybe tomorrow I'll show a code where you have learned from Ratan Samala Lex Pendrop scheme, Lex Frederick scheme. Yes. So can you learn that scheme? Who said yes? You? Huh? But he is not using neural network. That you can write the MATLAB program and do the coding and get the result. But if I want to learn the scheme itself, can we do that? No? So tomorrow let us do this. I have done this as a part-time work and it got published in some proceeding. So I'll do that for you. In fact, so Ratan has spoken about this equation ut plus u of x equal to 0, where your initial condition is ux is equal to u0x. Yes, and from the method of characteristics MOC tell us that the solution is uxt at time t equal to nothing but the initial solution translated to some other distance with at or at distance. And this is the exact solution, but you can do the numerical result schemes also. So the numerical schemes is your Lex-Frederick scheme. I will talk about the Lex-Frederick scheme. If I talk about this, so Lex-Frederick scheme is nothing but ui n minus delta t by delta x fi plus half minus fi minus half, where fi plus half is nothing but since it is a linear scheme, so you are having ui plus 1 divided by 2 minus 1 by 2 lambda ui plus 1 minus ui. This is the Lex-Frederick flux. Yes, you can write the Lex-Frederick flux in this form. If you plug this into this, you will get this scheme. ui n plus 1 is equal to ui plus 1 plus ui minus 1 divided by 2 minus 1 by 2 2 lambda 1 by 2 lambda ui plus 1 minus 2 ui plus ui minus 1. Can you check this? I don't remember, but I think it will come this scheme 1 by 2 lambda. It is correct here. So if I put delta t by delta x. Anyway, so basically if you are using this, I am no, this is correct. So if you are using this flux, then you will get Lex-Frederick scheme. So this has to be checked. And if you take fi plus half Lex-Fendorf, then you can write it as a ui plus 1 divided by 2 minus 1 over lambda minus 1 2 over lambda a ui plus 1 minus ui lambda a square. I think this is the Lex-Fendorf flux. So basically I will cross check this coefficient. So this is called numerical viscosity coefficient. These are the viscosity coefficient. Whatever Ratan has spoken, this is your numerical viscosity coefficient. We will try to write a code to learn this. So the idea is that we first generate the numerical viscosity coefficient using the given data and then learn it by simple MLP regressor. So I will write a simple MLP program and learn this. So then we will use these to approximate the solution. So here it's constant basically all the time. For whatever input you are having in the data, this is always constant, but it will change. It is not visible in this case because we are talking about the linear case, but when you go for the non-linear case, it will be your a will become u square. So it depends on the data also. Not A will be in the Lexman-Dorf case, AI plus half. A will become AI plus half, which will be nothing but Fi plus 1 minus Fi divided by Ui plus 1 minus Ui. If Ui plus 1 minus Ui is not equal to 0, otherwise it will be F dash Ui. So in this case, you can see that the wave speed is basically depending on the Ui plus 1 and Ui. So I'll see if we can do this, and I will. So you have seen the result by Lax-Patrick scheme yesterday. Did he do any coding? Where it? Huh? It MATLAB code. हाँ, MATLAB code. But so if you are taking this kind of solution, initial condition, how the Lax-Patrick was giving the result? Very dissipative. So it will be giving you very dissipative solution. And when you go for the Lax-Patrick scheme, it will give you the oscillation near the discontinuity. Yes. So we will see the same kind of phenomena can be observed by the neural network. So tomorrow I'll try to do this, and then I'll talk about the neural OD. Okay. Somebody is speaking. Okay, there, you too. So I think I can close for today. Tomorrow I'll talk about these two codes and the neural OD. Okay. If you have any question, you can ask me. Otherwise, Deepak is there, Anuradha is there. You can ask them; they can answer something. At least you can ask where I can be available. Okay. So those who joined online, I have to stop the sharing. Why it is stop sharing? Anybody from the online who wants to ask any question? No question. Any comment on tea? Coffee break? How was the tea? Eh? Coffee? Coffee was good. Anyway, hope to join with you tomorrow again. And tomorrow we'll be having lectures by Naveen. Professor Gowda from TIFR Bangalore. He will be talking about the same kind of stuff which Ratan Samala discussed, but in a different light viewpoint of view. Different point of view, sorry. And I will also talk about neural OD, and whatever I promised, I have to work on that. I'll do that. Thank you very much for bearing with me. Hope to see you again tomorrow. I will ask them to provide you black coffee tomorrow so that you don't fall asleep after the lunch. Okay, bye.